I just realized when I was driving here early on with Michal that one of my daughter's best friends is Polish. We live in Greece, but one of her best friends in Polish is Polish. And my son has got a rock band, and this is his T-shirt. Always buy his T-shirts. They make them all the time, and they're going to be famous one day. So one day, I'm going to sell this T-shirt for a lot of money. But the leader is also Polish, so we have lots of Polish in Crete, in Greece. So I'm going to talk about reflection. Before I do that, just one or two words. I write the Java Specialist newsletter, and this newsletter is a newsletter for people who already know Java, right? So I'm not going to show you how to print Hello World unless you want Hello World to print something else, like Good, Bright, Cruel World, or something completely different to what you'd expect to see. You know, there are lots of different ways you can do that. Now, think about that for a second, right? So that's a tutorial that we would do, but not, you know, how to get Docker installed on, you know, Ubuntu or something. We don't care about things like that. I want to talk about stuff that not everyone else talks about. And I've been doing it for quite a long time, actually. This newsletter has been going since 2000. That's almost 16 years, on lots of different topics. On last Saturday, I decided, why don't we start a Slack group, a Slack team? Now, initially, the people that are invited are people on my newsletter, and we've already got 1,000 people signed up for it. But I want to give you an invite today. If you want to, you can go there, tinyurl.com/gdansk-slack, or that little image there, and you can sign up. And if you sign up, I'm going to also sign you up onto the Slack team. Not right now, but tomorrow, tonight, or sometime. It's not automated yet, because, well, it wasn't such a bad idea not to automate it, because we actually immediately hit the limit with how many subscriptions you can have at a time on Slack. You know, we're like, boom, just submitted 200 emails, and it said, wait, you're spamming. So I had to email them and say, no, I'm not spamming. These people really want to be in the group. And as far as I know, I might be wrong about this, and if I am, please correct me, but I think we are probably the first Java Slack team, open Java Slack team. It's a free group. I mean, anybody can join, at least in a week or two. Once we figured out what we're going to do, then anybody will be able to join. You don't have to subscribe to my newsletter, of course, but you can, but you don't have to. So it's going to be an open group, and my wife says to me, what are you going to do with it? I mean, we only started this 48 hours ago, and we've already got like 1,100 members on it. So, and very interesting discussions as well. So it's not just like nonsense, hello, I'm here, but actually stuff that'll tickle your brains and make you wonder why you weren't on the group before. Well, because it didn't exist, that's why. So this is something hot off the press. I was preparing this in the airplane on the way over to make it available for you. So do that tonight. If you don't do it tonight, you'll forget about it. So just do it before you leave here today. Now, I'm going to talk about reflection. I like to compare reflection to opium. You know, the drug opium, not the perfume opium. And the opium is a very useful drug, I believe. I've heard, right? I've heard that if you've had a really bad accident and you're lying in the hospital and everything's broken and anything you move is painful, then you're going to want some of that stuff, right? But the problem is that you can get addicted to it, right? So with opium, you can do some amazing hacks. You can build some workarounds that sorry, otherwise would be very difficult. Now, what I do with this talk doesn't have a lot of slides. I'll show you a few slides, but then I'm going to go into different topics. And I just need to know, by a show of hands, how many of you are only using Java 7?
Only.
Only.
Only in the project, or only like in total, let's say.
Okay, so how many of you have never seen Java 8? Okay. Ask it that way around. Never seen Java 8. Okay, so it's not too many. How many of you have played around with Java 9? Okay, so Some people put their hands up for both of those, which is interesting. How many of you know what a var handle is? Okay, that's good. That's good. How many of you know what unsafe is? Whoa, that's bad. You shouldn't know what unsafe is, okay? That's not something you should know. Now, in the introduction, thanks to that, you mentioned concurrency. I recommend people do not use unsafe. I'm going to tell you a little bit about that because that's sort of one of the things people use for hacking. And I'll show you alternatives that you can use instead of that to get the same performance and be safe, or safer at least. Now, so thanks for that. How many of you, this is going to be a very dumb question, how many of you have written an equals method? Right. I mean, actually written it, not like just auto-generated it. Because, I mean, that's two different things. You use IntelliJ IDEA and you just say auto-generate this stuff and it just does everything for you and you never have to think about it. But yeah, okay, so we have these things with equals methods and hash codes. And of course, all of this code is tedious. Now, so I'm just trying to figure out from the group which direction we're going to go. As I said, I don't have a lot of slides, but I've got a lot of. I've spoken about reflection since 1999. So there's a lot in here which I can show you, but I just want to see which direction we're going to go. Every time I give the talk, it's slightly different. So you can do all sorts of crazy things with reflection. For example, what you can do is you can actually take any object and you can read the fields and you can call the methods and you can construct the objects with reflection. Now, there are some very good uses of this and some very useful uses of this. For example, you can set methods, or sorry, call methods like getters and setters automatically and programmatically. And so this can help you because because it means you can write very generic code that can be then called automatically. So you don't have to always hard code everything. It's more flexible. And they use this a lot in application servers and lots of different things. Now, but you can also go and call private methods and set private fields. Right, so here's a trick question. I want to see how many of you get this one right. Here's a private final field test. And this private final field test, what I've got is I first of all take the string class and I say get declared field on the value on the string. And then I say, I know that the value is actually a private, but I make it accessible by saying field or value.accessible, set accessible true. So even though it's actually private, I can now change it. Right? So I can actually change it. And then I say value.set on the constant string hello, and I change it to be actually the char array of cheers. And then I print out hello. The constant string hello. Right, so what do you think happens when I print out hello? What do you think will happen? You'll get cheers? Maybe. Maybe. Okay, the cheers is one possibility, right? Any other possibilities? So that's one option. There's another possibility. That's a very good question. So give me a Java version related answer. Okay. Okay, I know. I see where you're going with this. Sorry, my throat's a bit sore. I see where you're going. In Java 7, they changed string to also to not have a length inside anymore. It's always the char array is equal to the length. But very sneakily, what I did is I made the strings the same length by putting an exclamation mark into the hello. So actually, they are the same length. The Java 5 and 6 and 7 are going to behave the same way. But if for example, the hello, if the cheers chare was shorter in Java 5, it would give an exception. Okay, and now we've actually discovered a problem with reflection, right? What we've done is we've actually bound ourselves to a very specific version of Java. And if Java changes, if the implementation changes, then what's going to happen is that our code's going to fail. This is a problem with reflection. Well, with reflection on private fields. When you use reflection on public fields or public methods, it's okay because you're using the public interface anyway. But if you change private fields or you work with private fields, you have a very big danger that you might end up with exceptions, right? Okay, what happens if I run this code in Java 9? Anybody know? Pardon? Yes, well, let's try it out. Best way to see is to try it out, I guess. Let me just go and JUG. Gdansk. So here's my private final fields.java. Exactly the same code. Okay. String.class, get declared field value. And now I'm going to run this in Java 9. And I get a class, actually illegal argument exception. It's not a class exception. Illegal argument exception cannot set final byte array field Java lang string value to char array. You see in Java 9 they changed string internally to have a byte array instead of a string array. Okay, so as a result, when you try and set it to a char array, it says, wait a moment, it's actually now a byte array. Boom, illegal argument exception. So whenever you work with reflection, this is the danger. You can easily bind yourself to a very specific version of Java. And so when the version of Java changes, your code won't work anymore. And you actually see this often in libraries, APIs, or not APIs, libraries that you use, third-party libraries. They work with Java 7, Java 8 comes around, and sorry, it's not supported. Why not? Well, well, you know, we use some dirty tricks to do something, right? So this is all interesting and fun. I want to show you a couple of places where I used reflection to help me to do something that would otherwise would have been a bit difficult. Now, a friend of mine wrote a nice demo for JavaFX. And this is what it looks like, right? You've got, once it starts up, it's got like a whole bunch of different demos, and you know, things happen on the screen. And if you look at the top here, you can see that it's doing it at 61 frames per second, right? And in fact, all the demos he has, all of it, is done at 60 frames per second. So that's the same, but that's only because that's the rendering that they do. Now, interesting thing here is, if you look at this, what is the performance on the machine, actually? And the answer is we don't really know too well. We just know that we're doing 60 frames per second. That's obvious because that's the frame rate at which JavaFX is being updated. So it's supposed to be 60. If it's anything more, that's wrong, and if it's less, it's also wrong. Right? So you'll see it be staying at 60 throughout the whole demo. It doesn't change anything. But there are two different threads in JavaFX. You've got the renderer thread and you've got the user thread, application thread, and both of them might have a bottleneck. And so it's quite interesting if you look, for example, at the performance of a machine when you're using JavaFX, because if there's a certain type of animation, then the one thread might be under pressure and the other might not be under pressure. But we don't know by looking at this which one it is, or it might be both, right? So if you discover something which is slow, it's not always obvious to know where the slowness is coming from. Now, I want to go back to our presentation for a moment. I do have a few slides. And my methodology when I try and find a bottleneck is to first of all have a type of load test to identify the bottleneck. This might be a real system, or it might be a test. We then have to have a hypothesis as to the cause of the bottleneck. And this is very important to have this, because we need to always test that what we found is actually in fact the problem. It's happened many times that we discovered problems, or we thought there were problems, and after we fixed the problems, our performance stayed exactly the same or went worse, because we didn't actually find the problem. Right? So we always want to confirm that whatever problem we find is the problem. We then alter the application or the configuration, and we check whether we've improved the situation or made it worse, and whether our program still works. Sometimes by making our code fast, we break the code, because now we have race conditions that all of a sudden appear which weren't there before. And we keep on going until we have reached our target, whatever the target is. Now, if you look at, for example, a 4-layer application. Now, the 4-layer application's got 10% servlet, for example, 11% business component, 23% EJB, 56% SQL. But in the first scenario, you don't actually know what that is. So you go to Heinz's Slack channel and you say, hey, my application performance is terrible. And people say, go look at servlets. They're always terrible. It must be the servlets, right? So you go and you fix the servlets. And you spend about 2 weeks on making servlets faster, and you actually make the servlets 20 times faster, which is a massive improvement in performance. And the problem is, this is what we start with. Once we've made the servlets 20 times faster, we hardly notice a difference. It's about 9% faster. Not really a big deal. You hardly notice it. In the second scenario, you don't guess and hope to hit the mark, but what you do instead is you measure, and if you measure what the layers are, you see very quickly where the problem lies. You see, I've got a massive 56% of my time sitting inside SQL. So let's look at the queries. There's a query which is really bad. Put an index on the table, and 5 minutes later, you've got SQL being twice as fast, and actually you can notice the difference now. So we always look for the parts which are the problem and fix those first before we fix anything else. Okay, what we normally use as a guide to help us do the performance tuning is what we call the box, which is this sort of 4-layered application. The people are using the application is using the virtual machine, and the virtual machine uses the hardware. Now, it's very interesting watching programmers try and fix performance problems, because programmers normally start looking in the application. It must be an application problem. But very often we can actually make our program fast enough by simply adding more CPUs, or adding more memory, or buying a faster hard drive, or a faster network. And this of course upsets us as programmers. We don't want to be replaced by a piece of hardware, memory chip, or faster CPUs. We want to say, no, let me work on it for another 2 weeks and it'll be fast enough. But very often we can actually get great performance improvements by just upgrading our hardware, making it faster. It could also be the virtual machine, garbage collector, or number of threads. And sometimes it's lock contention. Now lock contention, the way that it shows up is that what will happen is that you'll be for example, your CPU won't be fully utilized, your memory won't be utilized, and still you won't get the performance that you want, that you need. I was doing a course in at Red Hat. You know Red Hat, the little company there, that small little company, and they had a benchmark that they were trying to get better marks for. Excuse me, please. Now, it was quite funny because they ordered a whole course, like a 4-day course, but actually it was 4 days of consulting, which I discovered when I got there, and there were only 4 students in the class. They paid for 10 students. They had 4 students, and they paid for 4 days of course. And all they wanted to do is to say, how can we find this bottleneck in this application? Because what would happen is they'd ramp up the performance, which was good. So slowly but surely the performance went faster and faster and faster as they added more load to the system. And then it stayed fast for a while. And after a while, it went slow. And then it stayed slow. And they couldn't find the problem. Now, an obvious problem is contention, right? Because the CPUs weren't fully utilized anymore. Memory wasn't utilized. The database wasn't busy. And still, they couldn't get performance to what it was before. Contention, right? Now, we started looking at synchronized. We didn't find it there. Then we looked at reentrant locks. These are far more difficult to discover than synchronized. Also couldn't find it there. And then for the last, one of the things I did, eventually I got really frustrated with the system. I asked them to try to give me 10 thread dumps before the problem and 10 thread dumps after the problem. So 10 before and 10 after. And then I sat there analyzing them, you know, trying to see what's going on. We actually managed to find with this, the problem was that they were losing semaphores. So they had a semaphore, for example, 10, and so with the semaphore you can allocate a semaphore, and then what happens is that you have to release it again. So you acquire it and you release it. But if due to some exceptional error you don't release it, the number of threads that can concurrently use the system gets limited. Or in that case, it was a number of connections to the database was limited artificially. So the performance was going fast. Semaphores were lost, and now they lost 20% of their performance. They couldn't get up again because those are permanently lost. You never get them back again. So the semaphore class in Java is a very primitive construct. It doesn't have a lot of depth. You know, it never knows who has actually acquired it. You get the number, but it doesn't remember who's acquired it. So it's impossible to know how many semaphores are actually in a system. If the system is busy, you ask the semaphore how many have you got available, it says 0. I don't have any. Because they've all been given out. So how many do you give out? Well, I don't know. Who do you give them to? I don't know. When are they coming back? I don't know. And you know, a little thing like that caused a lot of problems for them because the performance simply wouldn't go back. And I've had it quite a few times the last few years where customers came to me and they said, we want to, we're not getting, our system's not fast enough, it must be faster. And you look at the garbage collection logs, that's something very useful to do, and the GC logs said it's fine. I mean, there's hardly any GC going on. CPUs were fine, you know, everything's fine. But if you look carefully, you discovered log contention, either application logs or synchronized, reentrant locks, semaphores, one of those things. This sort of thing is very hard to predict up front where the contention will come from. It's one of those things that you really need to discover on a running system. You can't discover this just like that. Now, what else I want to say with this? Oh, it's another thing to do with concurrency, and that is I've quite often discovered race conditions in customer systems where something goes wrong and then the system doesn't work anymore. But I've never had a customer come to me and say, Heinz, I've got a race condition, can you help me? Never. It's always like, can you help us with some consulting? We can't explain what's going on. But they never know they've got a race condition. So it's quite interesting because you can never sell your skills as a race condition finder because no one will buy it. No one knows I've got it, you know. But it's actually quite interesting how often it appears. So the one time we had an out-of-memory error that happened because of a race condition. There was an infinite loop inside a hash map, and that caused an out-of-memory error, right? Because if you resize a hash map whilst you're adding an element, you can get an infinite loop inside due to the race condition. Okay, now let's look at some code. So our demo ran for a while. We had no idea what the threads were doing. Now we could do, you know, go with JVM, connect to it, do a profile of those two threads and see which one's using what. But I thought, let me rather use reflection to dig into the right place and find the right place where the problem is, and then attach myself like a leech. You know, those blood-sucking leeches, attachments like a leech to the thread and suck out all the information out of that leech. Okay, that's what I wanted to do. And what you can do, there's a class called threadmxbean in Java. With threadmxbean, you can find out what a thread's CPU time is and what a thread's user time is. So CPU time is a total time, nanoseconds, that the CPU has been spinning either for system or for user work. System work is things like context switching, disk I/O, network I/O. These are all examples of system time. Normally in your CPU graph, that's the red bit. The red bit is your CPU graph, is your system time. And then the green stuff, which is the good stuff, is your user time, right? So we want to have high user time in comparison to system time. And we also want to make sure that our user time isn't too high in comparison to our CPU, to our elapsed time. Elapsed time is your wall clock time. So for example, if I've got two threads running, now there are two threads running in JavaFX as far as I can see, and it could be more though. They could have a pool of threads and increase it, but for now we've got two. And what I want to do is I want to measure what's the ratio of user time to elapsed time. So for example, if I go over 30% of user time over elapsed time, I need to look at that, because that means that my system is under pressure whilst doing this operation, whatever the operation is. And it might be something very simple, something that's not obvious at all. But it's good to know the number to say, okay, it's now above my threshold. Or if the rendering is more than 30%, for example, set a target of 30%, then you've got a problem there. You need to optimize your rendering. Maybe not have as fancy graphics. Make sure that everything is set up correctly. Okay, so what I did was I attached myself to this by reflection. The first thing I did is I wrote a class that called Thread Performance Testing FX Launcher. And the way this works is that it sets up the watcher, and then and then what it does is it then calls the next main method, right? So basically, it delegates the method call to it basically attaches itself to to a process before you launch. In other words, I'm launching it from here. In other words, if you look at this call next main method, here I'm going to say look for the main method, and inside the class that's next on the argument list, and call that. Right, that part's pretty easy. This is now the very latest early access version of IntelliJ, by the way. And I just noticed that they've added a little bit of help to show what the strings and constants are. So name : main. That's like from other languages, Kotlin and stuff. From one is daemon true. So whenever you've got like constant strings, they show you parameter labels. It's the very latest version of IntelliJ. It's the early access version, 2016.3 or something. And what happened is, I was at the airport in Athens, and I thought, let me just make sure that everything works. And I tried to launch IntelliJ, and they said, oh, it's expired. Haha. They always do that to me. Now I've got a perpetual license forever, but not for the early access edition. And so I quickly downloaded it whilst I was actually going through the X-ray machine. I was like downloading this thing. But this is actually the first time where that's happened to me, where I'm actually happy, because this is very cool. Having the parameter names there is going to make it much clearer to maintain code you don't know that well. All right, so let me show you how I go and find the different components here. First of all, what I want to do is I want to look for the thread pool executor that it's going to do my quantum rendering. That's the rendering of the actual graphics. And you see there's a method called grab pool over here. And inside here, I'm looking for a class with this specific name. Now, you can obviously realize that this name might change in the next version. It might become, I don't know, oracle.com. or I don't know, something else, something.oracle or IBM, I don't know, so change it in some way that it's, or Apache, that it's no longer this, but it's a different name, all right? So this is only for this specific version of Java. It's only for Java 8. Java 9 might not work. In fact, it doesn't work with Java 9. You can get it to work, but it's not so easy. So, I load the class. I use the current threads context class loader. If you load a class, you're supposed to do that. You're not supposed to load it without that. Otherwise, it's going to use the current class's class loader, which might not be the right one in an application server context. I then look for a method called getInstance, and the method is on the class getInstance, right? It's actually, I believe the method is a public method, a public static method, but the class quantum renderer is not public. It's a package access class. Because the class is package access, I need to make all the methods accessible true. Right? In fact, there's no such thing really from reflection as a non-public class. The class is always public. You always load a class. But you can't access the methods if it's a package access class. So what I do is I look for the method getInstance, and I say method set accessible true. So like in my string, I'm not saying I don't care about the fact that you said it shouldn't be accessible. I'm overriding you, and I'm going to get it anyway. So I set accessible true, then I say getInstance method.invoke, and because it's a static method, I don't have to pass in an instance of the quantum renderer to get the instance back. And so when I call getInstance on that, it returns the thread pool executor. Okay, and the quantum renderer pool is actually an instance of a thread pool. It's a subclass of thread pool executor. So it's just, you know, if you've read Brian Goetz's book on Java concurrency in practice, a very good book. You should read that. It's a bit old by now, but it's a good book anyway. Then you'll know how to configure these things, and you'll find it much easier to understand how this class works if you know the book. Now, quantum renderer thread, I then say grab thread. Now, grabbing the thread is a little bit difficult. Before I do that, I want to ask some questions for you guys. Assuming there's a thread pool, and assuming that I want to discover the thread in the thread pool, what's the way that you can discover it? How can you get the thread from the thread pool? Pardon? What do we mean in the same thread? Oh, in the same thread group. Yes, okay, yes. This is one way, is you could go by the thread group, right? And you could sort of look for the name, and look for a thread with a certain name or pattern, and then find it that way, right? But thread groups are not really used that much. So basically, you have to look at all the threads in your thread group, all of them, right? So let's leave thread groups out of this, because that's probably not going to be well, it is a way, but it's maybe not the cleanest way of doing it. So I'll tell you my idea. My idea was you pass in a callable with a thread array of size 1. In fact, you can even, no, you don't have to do that. You can just pass in a callable of type thread, right? And the callable of type thread returns a future of type thread, and then all that the method does, all the callable does, is it returns thread.currentThread. This way I can find the thread from the thread group. Let me show you. Discover thread. So I want to find the thread. So let's say I want to say, for example, executor service pool equals executors.new single thread executor. I want to find that thread, that single thread in here. I'm going to say pool.submit and I'm going to return thread.currentThread. Okay? So that's a callable. This Java 8 syntax, it's actually equivalent to new callable, the whole call method returning the thread. So that'll be the same as lambda. It's the same as this, right? So having new callable thread and then public thread call throws exception, return thread.currentThread. So, but of course, I mean, I think this is neater. And then I can say thread equals dot get. Right? And a bunch of exceptions that can happen. And this way I can discover the thread that's running inside the thread pool. Okay? And so I can let's try something. Let's say pool.submit. Hello. Okay. So it's printing hello from the thread in thread.currentThread. So it's going to print out hello in the thread, the current thread, and it should say hello in thread pool1 thread 1 5 main. Okay. The main is a thread group, so that's what I'm saying, that all the threads are going to be in the same thread group in most cases. You know, it's not going to be a useful way of doing it. It works, but it's not the best. And now I could actually say thread.stop. It's going to kill that poor thread, most likely. Well, maybe not. We'll see if it actually dies or not. We'll say hello again afterwards and see if it can still say hello. Well, something's gone wrong, right? Didn't say hello again. It's very upset with us now. Of course, you should never stop a thread, so I'm going to delete this code again because that is very bad. But my point is, this is how my thought was. I'd simply pass in a callable, and it gives me back the thread. So I can now say, I can also say print out the value of thread, and you'll see that it actually is that thread that comes back. Okay, so the thread is that thread that's inside the pool. Okay, so but that didn't work, right? My great idea didn't work because the quantum renderer they actually shadow the submit method, and they submit their own objects into submit. So if you submit anything besides their objects, it fails. It throws an exception, or just ignores it. Can't exactly. So that didn't work. What I then did is the following. I wrote. I know that inside the thread executor there's a field called workers. It's actually a set of workers. And so what I did was I looked for the declared field called workers. Okay. I said set accessible to be true. I then said workers field dot get quantum renderer pool. So I would get the set of workers, and I'd just get the first one. And now there could be more than one, but for now I'm just caring about one. So object worker equals worker.iterator.next. So just get the first element. And inside the worker is like a wrapper class that holds threads and a bunch of other stuff as well. Inside that, I would then look for the field called thread, and again make it accessible true, and say thread field.get the worker. So this is the way that I found the worker. For the FX user thread, I did something a bit easier. They had a class called toolkit with a method that was called get FX user thread. So that's a bit easier to discover. And so I just made it accessible true, and I returned that. That was quite easy. And then what I could do is I could render, I could measure the time of before and after. And of course, you can then have you can then show the saturation of user time or CPU time versus elapsed time. So let me show you how this runs. So let me run this again. It was actually running in the background. We just didn't see it. Okay, so this is a star demo. You can see a lot of graphics and text scrolling and stars flying. And you'll see now that my quantum renderer utilization was 13%. Okay, just be careful because it's still doing it. And the JavaFX application was 5%. So the application thread was almost nothing. To calculate where the stars go, it's like minimal. And to measure to the drawing was 15%. So it also wasn't too bad. And then this is now a different demo. Okay, right. Let me just do. Okay, let's look at this one. This one actually has CPU quantum 23% and user 4%. So this is a really heavy thing to draw. You can actually see that drawing is taking a bit of strain, but it's still 60 frames per second, right? This one, have a guess. Let's see, 22%, 19%. So this one is sort of equally heavy, both on the calculation side and the drawing side are about equal. So this could be a good benchmark to say, if 20% is probably our limit on both. If you have 20% on either, you're probably going to have okay performance. If you go above that, we are looking for trouble. We have an application which is not that great. This doesn't look like it's going to be very expensive. 12% and 4%, 7% and 4%. Even though the graphics are quite fancy, I think. 4%, 8%, 4%. It's actually not taking any strain at all. Most of it is done in the GPU anyway. Of this 9% and 5%. Okay, so each of the demos has different values. This one looks complicated and expensive, but it's not 9% and 5%. Again, the GPU is taking most of the strain, and then just a bunch of stuff done by Chris Newland, the guy that wrote the JIT Watch. And the funny thing is, he thanks everybody that he knows. And I was looking at this going like, what the heck is my son's name doing in there? He's a rock star, But then I realized after a while, there's my son, Maxi Kabutz. Then I realized after a while, my name's also in there, and I did nothing for this, so I guess everybody's in there. So this was quite interesting. And then I applied this to some of the demos that they gave us with JavaFX, right? Let me show you one of those. Go to JavaFX samples. Nope, that's the wrong one. Java 8. Okay, so this is now a lovely demo that they gave us to show us how cool JavaFX is, right? Yeah. So if you want to build a nice GUI framework, there we go. And you can see here that it doesn't take any strain. I mean, it's like application thread is 2%, quantum renderer is 0%. that's what we would expect, because it's just a web, it's just a page with nothing really happening on there, you know. Combinations. You're looking at again, nothing. 0%, 1%. Obviously, if I move around, it's going to be a bit like, let's go between the different pages. Like, I'll just go backwards and forwards a bit, and we'll see if it takes any strain. Nah, no strain. It's like 8% user and 1% application of the quantum renderer. So it's nothing. And then, let's look at this one. So if you don't know if you can see at the back there, probably not. That's the quantum renderer is sitting at 35%, 34%. Now you saw what the quantum renderer could do in Chris's demo. Could all those graphics and spinning tops and could anything, you know. And that shouldn't be sitting at 36%, right? The application is 22% actually. So that's sort of, let me just make it a little bit smaller so I can just fit around. So 22% for user and 36% for the quantum renderer. There's something fishy going on here. I mean, it's just sitting there, right? It's not doing anything. Just sitting there. Why is it taking so long? Why is it using so much space? Any ideas?
The spinning thing, right? That's the only thing with it.
The spinning thing. Right, there's a progress monitor spinning thing that's going round and round using 36% of one of my cores. Right? Just to make sure I don't get there any faster. Right? This one's fun. This is now the whole kitchen sink, they call it in English. The demo to show how cool JavaFX is. And now, no, this is not working. But 93% saturation on the quantum renderer. 93%. Okay. The user thread, 6%, nothing. And if you look at this lovely, I mean, you can even see it when I'm trying to scroll it. Okay, I don't know if you can see it, but it's like when it doesn't react very well. Okay. And ooh, another progress bar. Whoa, 1, 2, 3, 4, 5 progress bars. Whoa, this is fun. That's your lesson learned. Don't ever use progress bars until they fix that. Right? But anyway, the thing is, you can take this hack to hack onto the threads, attach yourself like a limpet onto the threads, like a leech, suck out all the information. We can also do one thing which I did with a friend of mine, is you can actually get the number of bytes that were created by the thread as well. So you can find out how many bytes every thread constructed, allocated. And it's funny because if you look at the thread MXB, it's not actually one of the properties that it offers you, but it is there. You can find it. If you look at my newsletter, it's there. Or you can just dig around it, but you can see it in JConsole. So this is useful because it can show you where problems are. Now, obviously you discovered it, and I think that is the problem. That little spinning thing. It needs a bit of work. But and I just attached to it with reflection, and I often use reflection, but I use reflection as a temporary hack, so for temporary workaround to to discover what is wrong with my system, and then I throw away that code. Usually, I don't keep it around because if I keep it around, I'm going to create a dependency onto that very particular Java version. I don't want to do that. I want to make sure that I always that my code is always going to be compatible for future versions. And that's one of the reasons why Java is so successful. You know, I mean, on all the indexes, Java's #1, which is surprising because Java's got a horrible syntax, and I mean, it's so verbose. Everything you have to say 2 or 3 times. It's terrible, but I can take Java from 1.0 and I can run it today in Java 9, and it still runs. Okay, most stuff still runs. Whereas I can't take, you know, Scala 1.0 and run it in Scala 2.0 or 3.0. It's just no chance. Okay, forget it. You have to migrate, and for big companies, this is very important. I mean, some people have you know, millions of lines of code, or tens or hundreds of millions of lines of Java code. They don't want to know about, you know, hey, we're going to do this new thing, we're going to have named parameters, and now all you have to do is change all your methods to have names on all the parameters, and then you'll be fine. You know, no, you can't change anything, and that's the strength of Java and its weakness, because anytime something new comes out, Java can't keep up. I mean, you know, like lambdas took forever to come out, you know, to get into Java, even though they've been around in the languages for decades. For Java, they came out just like the last one on the block. Any questions? I've been speaking a lot for the last hour. It's time that you ask something.
How to do that situation when you get from another thread pool more threads, and then what? Like because or maybe how to use that, get it in that way information which thread makes a trouble.
Oh, right, okay. So your question is about, let's say I've got a bunch of threads. How do I know which one's actually the culprit, right? Well, you can already see it in a profile, right? The problem with a profile is that attaching a profiler to a system is very risky. The system might crash and burn because the profiler has some error and the whole system falls down. So this is why what I do is I sort of, I just inspect it. And I say, I've got all these threads. In fact, you can look at all the threads if you want to and just do a diff between now and 10 seconds ago, who's used the most CPU time. And from that you can actually see it. And you can then very easily find out which threads are the most busy threads. Or the ones which are not busy, which should be busy. Or which have a high system time, which is the difference between CPU and user time. You want to find all those threads. Any other questions? Sorry.
So round of applause for Heinz.
Thank you very much.